Hello, good evening, everyone. Shall we start the event? My name is Chinthaka Premachandra, and I'm from Shibaura Institute of Technology, Tokyo. So before I start the meeting, actually, I got some request from Mausa Electronics Company in Sri Lanka. Uh, they asked me to ask their participant to submit a survey from the company. So I have put the survey on the chatting, so Zoom chatting, so you can follow it. Okay, please follow it. It's just for the participant from Mouse Electronics, so maybe for not for others. Okay, please, others do not have to care about that. Okay, so I think it's the time to start our, this event. Maybe the event organized by Sri Lanka Robotics Meetup event name, I think. So organized by IEEE RA Society Sri Lanka section chapter. I think first of all, I would like to thanks to Dr. Sagar and some Mr. Adhikari and many other members in the Sri Lanka IEEE Sri Lanka section, and especially in IEEE RA group in Sri Lanka, RA chapter, to arrange in this event. And again, additionally, I would like to thanks to inviting me take part this event. Okay, so I think it's time to start our event. So I'm I'm going to make some presentation related to some works done in my laboratory in Tokyo. So the the topic is vision-based autonomous flight control approaches for UAV. Okay, I will go by slide. Okay, so first of all, I would like to introduce myself a little bit. And actually, I'm originally from Sri Lanka, but after high school, after A levels, I went to Japan. The reason is I got a scholarship from Japanese government for my high studies. Then I completed my B.Sc, M.Sc, and Ph.D. in Japan. Right now, I'm working in the Shibaura Institute of Technology as an academic staff member. So my research interest includes image processing, computer vision, and some intelligent transport system and some robotics system, especially more aerial robotics. Okay, so at the beginning, so today's topic is the vision-based autonomous flight control. So as you know, then in the world, it's the UAV is becoming some hot topic. So, and here in this presentation, I will talk about vision-based autonomous flight control. But first of all, I would like to talk with you. I would like to mention that why we use vision-based. Why vision? That's first of all, I would like to mention about this some information. As we know, vision-based is something we have to install a camera in the machine. So in the UAV. So that means when we use a kind of a camera that we can get a precise information, we can acquire the precise information by image processing, and that we can get some information in more details rather than other sensors like UW sensors or depth sensors and some others. And so when you conduct the vision-based autonomous flight, that we have to install the camera on the UAV, but at the same time, we can use this camera to do some other purposes, like some other operation, like aerial, data acquisition, aerial, photography, or some other purposes as well. And on the other hand, recently that, if you have some experience in UAV, some development, but you may know that sometimes when we make a UAV, sometimes we have to, when we are going to add some additional hardware, we have to care about the weight and the size of the hardware. So recently, as you know, that compact and lightweight UAV installable cameras and image processing hardware are commercially available. For example, like the Raspberry Pi or some Arduino, we can install in the UAV for image processing purposes. But so Raspberry Pi is the, I think, best according to our experience. Maybe some other hardware also available. So, however, that when we use when we use cameras, onboard cameras, that the point is for, autonomous flight purposes, that most important point is to have some real-time image processing. Some image processing should be less than, 20 millisecond per frame is most important to have some, smooth autonomous flight control. This comes from the, flight control side. In the control side, that it requires something like this condition. So I think in this today's story, we have three main stories. The first story is the vision-based obstacle avoidance of hybrid aerial terrestrial robot. Actually, this hybrid aerial terrestrial robot is a robot that we made in my laboratory, but we control it based on vision. So first of all, I'm going to talk about a little bit. First of all, I would like to introduce this robot a little bit, and then I will talk to you about how we conduct vision-based autonomous flight. So it's, this is a robot that, robot which can automatically change into the ground movement to the aerial movement and vice versa. This is the, the main concept of this hybrid aerial and terrestrial robot. So actually, with this hybrid aerial and terrestrial robot, that we can achieve something we cannot achieve with, robot itself as a, terrestrial robot, or with either with the robot as an aerial robot. For example, when you look at some wheel robot, that for when we are going to use a wheel robot for some operation, so we have said some, in the case that we want to send a place a little far from the where robot is. So in the case of aerial robot, we can send it by flight easily, but in the wheel robot, maybe we have to take it by some another vehicle or another, another robot, or I don't know, in another way. So in that case, but however, if you can fix some aerial functions to the, the flight function to the wheel robot, that we can send it to the place easily, far place also a little bit easily, rather than without having flying functions. So that is what we are going to do in this project. In here, that in this slide, maybe you can see some in the up area, that in the top area, that we mentioned about the strong point of each terrestrial robot and the aerial robot, and the bottom area. This show there's some some weak point of each robot, and at the end, that if you could combine these two type of robot, we can extend their operational abilities further, as well as we can reduce some disabilities. So this is the purpose of making this robot. So its concept is like that: it's terrestrial robot and aerial robot. We combine together, we have some hybrid aerial terrestrial robot. So this is a kind of machine we made in my laboratory. So you can see that it includes some wheels as well, and of course it includes the drone functions. Drone means the UAV functions as well for having flights. So to make this robot, that we have to maintain the stability for the axles. To maintain, so this when it have flight, that it should maintain its balance. But when it have four legs, like with the wheels, so sometimes it makes some unstable situation. So we have to maintain the stability for the axles. The framework of aluminum was sandwiched between the shaft and wheels, as shown in this slide. Maybe you can see with dumb technique we used to solve this problem. So additionally, maybe you may know that sometimes when making this kind of robot, if this robot have a flight and then it's going to be landed, and then maybe when it touch the ground, maybe there's some huge shock. Some depend on the the control method. We can reduce the shock, but however, still there's some shock. Due to this shock, that robot can be broken down easily. So we solve this problem by using dampers and spring shock to to the chassis while landing are suppressed. So we made, actually this technique was made having some lot of trials and errors. However, now the robot is very stronger, the one in my laboratory. So we use it to make some research projects. So I would like to show you some video of this. This is a video of robot having some flight. So actually one of our students want to have, maybe as you could see that, maybe you can see that this in this robot, we have not, we can add some motors to, motors for the wheels, but here we have not had, that this is the situation that we have not had. So one of our students want to have some, ground movement by flight mechanism. So he is a kind of project done in the laboratory. So let me show you some small video, but still the results are not successful. So it is moving on the ground, but still, the results are not successful. It needs more, more research to improve it. Okay, so I think this kind of research still got some works going on in the laboratory. And another thing is another project related to this robot is very much related to today's topic, the obstacle avoidance by flight. Here, that obstacle detection is done by vision-based method. In the future, we are going to have this robot. We are targeting to have some operations in the disaster fields or something like that, while sometimes it can have operation, it can conduct operation while moving on the ground, and sometimes it can have operation while flying on the air, and by avoiding obstacles by flight, like that. So here's some works done to show works related to the avoidance of obstacle by flight. Here, to achieve this, actually we have to add some additional hardware to the machine. So this is the left side of the slide show that some additional hardware we add to achieve this target. Here, that obstacle detection unit include the camera as well as the IMAP-2 hardware, which is for image processing. Actually, it's IMAP-2, a very small type, lightweight hardware, which have been developed for car electronics. And the right side, that in the almost middle of the slide, you can see that here we have had some another microcontrol to decide the flight, flight variables, maybe the control variables for flight, and these information are sent to the flight control of the robot. So actually, about this kind of system, I'm going to talk to you in the next project I'm going to present today. So here, that all this hardware are installed in the machine, like that, all are in the machine. So when we install this kind of hardware, that the most important point is what. Let me show you some important points. The hardware should be lightweight and small size in size. And when we install in them, the balance of the robot is extremely important. The gravity point of the robot should be kept on the midpoint of the robot. This is roughly, we have to keep it. Otherwise, we cannot have, if the robot have the balance, do not have balance with other hardwares, we cannot have very smooth flight. When the flight make little unstable. Let me show you some, the experiment we did, obstacle avoidance by flight. It's like this here. It's completely automated. Now is, ground movement also done autonomously. The method I showed you just before, and you can see that it's it can avoid obstacles by flight, maybe from another direction. Actually, this experiment was done in an indoor environment in Tokyo. We are not allowed to make flight outside, so sometimes we do experiment in the indoor environment. So I think now I'm going to talk about some another project we did it in our laboratory. Here is it vision-based autonomous hovering and landing control. Actually, in this title, under this title, I'm going to talk a lot of things regarding to the topic today. So first of all, I'm going to show you some of the problem setting here, that what is the problem we are going to solve. Here that, here there's the robot moved to when this there's some UAV. If the UAV found some landing spot H mark, the UAV automatically move towards the landing spot and then conduct some hovering before landing, and then finally landing. This is the problem that in this project. Okay, so to carry on this project, what are the problems works we have to do? This is very important. So maybe you can see some work to be done here, maybe in this slide. We have to make a technique to convert the manual mode to the autonomous mode, vice versa. Okay, then we have to consider the detection of the landing spot from the UAV camera images. And then actually while doing so, then we have to we have to control the robot to, conduct the, moving towards the landing spot, as well as making some, hovering there. To do so, we need to, sorry. So we have to, sometimes we have to get some, we have to convert image information to the real world measurement, like for example, image pixel measurement to the real world measurement. So after that, the autonomous control of the UAV can be achieved following these measurements. Okay, so in the autonomous control, then moving towards the landing spot and hovering on the landing spot, and landing is conducted. So if you have experience with the UAV, you may know that generally in the how a UAV works. So in the transmitter, some remote control transmitter, generally we have it. There are different type of one. Then we can send some commands to the drone through this transmitter. It sends some signal to the receiver. Receiver get, actually it includes generally this. There are 4 main channels for roll, pitch, and yaw throttle commands for command movement for commands. Okay, commands of those roll, pitch, yaw, and throttle. So these commands come to the receiver, then receiver and just transfer those to the flight controller. And flight controller is a kind of heart of the UAV, and flight controller send this information to the motor controllers, which are on the UAV. Then motor controller control the control the motors to have the flight that come from the commanded by the remote controller. Okay, so this is something very general idea. Is a flight controller there is a heart, and that it decide which command go to the which motor, which command go to the which how much, and which which signal go to this which motor, like that. So this is the way that it happening. So in this work, so again, so return to the original story. So here that first I'm going to talk about the make techniques to convert manual mode to the autonomous mode. Actually, when we are going to do some work with this UAV, we have to keep the manual mode. Even it should be under control of the human being. So we cannot give it to have complete autonomous mode. Then it's going to be very dangerous. If there's some mistake, it's going to be a quite accident or something like that. So in this technique, these are some hardware we use to have this technique, and for the process in this project. So the whole hardware is this receiver. It's on the receiver, and the multiplexer, and Raspberry Pi, a camera, and Raspberry Pi. So here that in this project we use we additionally add some multiplexer to this kind of some switch, maybe switching mechanism to change the to convert the autonomous mode to the manual mode, and vice versa. So this is a real machine we made to had this experiment. So So let me talk to you. Let me introduce you how we do it in shortly. So here that is is a generally it is under the drone is under the manual mode. Okay, so the command from here that goes to the flight controller. But in the case of that, if the system detect that landing spot, then it converts to the autonomous mode. Of course, here we can forcibly return it to the manual mode as well if we want. We have kept this under the human being who control the who manage the who control the who make the piloting. Okay. So there's a story about behind that autonomous mode, to how to convert autonomous mode to the flight mode. Sorry, manual mode to the autonomous mode. So there are here some in details, but I'm going to skip here. This is a machine in with the bigger picture. Maybe you can see that mode control by a video. You can see now when it detects its mark, it will it's already the spark is detected. Now it is under the autonomous mode, but here then change into the guy here already changed into the it changed into the manual mode again and make it landed. But later on that is automatic. I will explain you how it land autonomously. Okay. So to land, then I'm going to talk about the detection of this land spot from UAV camera images. So here we are, as I mentioned, now that just before that, the image processing is done by Raspberry Pi. And here we use a wide angle camera. For example, if you're interested to do some project with this, some vision-based camera with the UAV, I would really recommend you to use some camera with a wide angle. Because generally that is here, the camera we use has an angle like 160 of view, 160 degrees of view. But generally this is like 80 or maybe half of this. So if you use a wide angle camera, then easily do this kind of work because it can capture the information, of the wide area. So here that the camera is installed on the robot with a gimbal. Okay, so because we have to keep the camera in the horizontal when UAV make flights, it is on the flight that the camera is kept horizontal. We use a gimbal for that. So I'm going to talk to you a little bit about the algorithm, this landmark, this landing spot detection algorithm. Here we at the first stages is we use some very simple image processing. This image from camera, and we convert the image to the grayscale, and again the grayscale convert to the binarization. So after that we try to extract some points, some corner points from the images. This image, we try to get the corner point of the H mark. There should be 12 corner point which have some relationship. We use the relationship. I'm going to talk to you now. So after getting these are the one feature with stronger, feature corner points we used as one feature, and another feature we use when you see this H mark, the contour has two lines between the two longest ones. For example, like if you consider these two longest one, there are 5 lines in between these 2 lines. This is another feature we use here to capture. And so additionally, we use that if the 2 lines are at least 4 times longer than their direct neighbors. This means these 2 lines means here 1 and 5 are, 4 times longer than their direct neighbors, like that. This is another feature we use. And then we use this simple feature to capture this landing spot, because our target is to reduce the computational time. Of course, to capture this kind of landmark or this mark, we can use a lot of some AI-based method or neural network or CNN or ANN or any neural network as well. But point is, sometimes it is still difficult to have real-time detection. So after detecting this H mark, this kind of some example images of H mark detection. Of course, after that we get the the middle point of the mark. So once we detect H mark, we capture we calculate this, the head of the H mark, as here we call X max. After getting this head of the H max, then we get the region of interest. So once we capture the region of interest, so in the next frame, you just process the area, almost belongs to this region of interest. So through this, we can again reduce the computational cost, computational time. So I'm going to show you some video about this, landing spot capturing by image processing. So the left side is the original image, and it including the the middle point of the landing spot, and the right side you can see the ROI. So this is here that ROI. That as you can see that this landing spot is completely almost detected. So again, if there's a barrier like that in the left side, you can see, then it's not detected. But after removing the barrier, then it's again detected. So this algorithm works well. Later, I will show you that through this algorithm, we could, we could control the robot, or we could achieve the autonomous flight. So here we could achieve this within the computational time was 12 to 22 milliseconds. And here this slide, I can show you some computational time per frame in millisecond here in the versus distance between camera and landing spot. Here, if the here in this x-axis is the distance between camera and landing spot in centimeter in the real world. Okay, so here that computational time per frame in millisecond when according to this distance. As you can see that if the distance is near this, you can please focus on this blue line. You can see that, and when the distance is far, so it's the computational cost is very low, becoming low. This reason is that that's computational cost is depend on the the number of the pixels represented for the by the for the H mark. So this landing spot. So if when the number of the processing pixels are getting decrease, so the computational time also decreasing. So here in the blue, I want you to focus on the black line. You can see this black line, that length of the S max of the H max pixel, that is this length. So this is the here in the x-axis is the distance between camera and landing spot. As you can see, it says here that when it like 10 centimeters, that H mark is not detected because the camera is it's too near, so it is not detected. So because the image the images H mark doesn't appear in the images when the distance between 0 to 10 centimeters. But over the 10 centimeters, we can detect it like that. This is the length for this black line represent the length of the the head of the H mark. Okay. Or we could get some information regarding the computational time. Okay, now it's okay. So I think another story, in this project, another target we have behind us was to convert the image pixel measurement to the real world measurement. So I'm going to explain you a little bit about it, not in very much detail, but for certain details. So I think to achieve at the end, so after having this conversion, everything, finally our target is to achieve the horizontal control of the flight and some landing. But to achieve horizontal control, we need a centimeter value to function the system. So here the converting the pixel distance to the real distance is very important. We need a formula for that. In this graph here, that it's interesting graph that I think it shows the it is versus distance of H mark to the center in pixels. Like this is the image from the camera that you can think that the machine is, or it is this image from the from a UAV camera. Okay, here forget about this UAV. So, however, that is if you think that the distance of H mark to the frame center in pixels here. So in the here in the right in the y-axis, the horizontal distance of the camera to the H mark in centimeter. Here is the pixel distance, and this is a kind of centimeter according some real world measurement according to this H mark. But here you can see many lines. This means that it's depend on different head. When the robot have 40 centimeter head, this is the relationship. When it is 50, is the relationship. I think it's like this. Okay. When it's go to the 120, this is a relationship. But as you can see, but here is now sometimes we have done a lot of assuming here, because you can see when we make this line, we did some assuming, because it's kind of not, they are not coming with some exact straight line, these all the dots when we take data. Actually, this graph is made by getting some practical data. So
we have, can you hear me?
Sure.
Yes, you are good.
Okay. Audible. So do we have guest today?
Sorry.
We have one guest, Kalpana.
We have only Kalpana today, but she won't be talking in the meeting. She'll be only participating as an observer for today. So with that, good evening everyone. I welcome you to the 42nd Marga meeting. But just in case, Kalpana, are you okay with introducing it?
I think, sorry, maybe some some local talks came out, but I make it mute. Okay, so let me return to the presentation. So here that maybe I just want to focus on you can see that distance of H marks to the frame center to pixel. Here you can think this is the pixel values, pixel distances. These are kind of real world distances in centimeter. So this is kind of relationship we got according to the distances. So okay. So however, we can see that this is the each line represent the each heads of the drone. Okay. When the drone come to the 40 centimeter of head, then it is the relationship is pixel to centimeter relationship become like this. Okay. Then when it come to 120, it become like this. So you can see this relationship. And so however, that maybe we can get rough relationship here. Finally, what we did is we made some more conversion. So we get here, maybe we what we did is we got the ratio between, that means the inclination of each these lines. We calculate, and each line is represented each dot here. Okay, we got the slope in centimeter pixel ratio, and this is the head. So now we have an equation. We could have this equation. This is a pixel to centimeter conversion. Yeah, could be done with this equation. So we could get the relationship between some centimeter pixel conversion here, centimeter in between centimeter and pixel in the real world. But here what we are talking about, I'm talking about the in the xy plane. Okay, not Z direction. That means altitude is not included here. So to achieve finally that autonomous control of UAV, I think we have to final target is to achieve autonomous control of the UAV. Here, okay, the head, is measured by using a size of H mark in images, or we can use some pixel information of H mark to measure the head, or we can use a separate, ultrasonic wave sensor or other sensor to measure the head of the, UAV here. So, and whatever method we can apply for this. So finally, that I'm going to a little bit give you some little information about how we achieve the control. Here, XY directional control is done by PD control for robot to come to the top of the landing spot, that means mark, and then hovering control and landing control is done by PID control. Okay, So finally the control process also computed by onboard Raspberry Pi computer. All the processing in this system is done by the Raspberry Pi computer. So I'm going to show you some experimental video hovering, and here this is going to be the hovering method. Here, actually, the hovering is, you can just focus on the hovering. This next video, I'm going to show you the, hope you could see that it could, have some hovering on the landing spot. Even the landing spot, when we change the landing spot, that according to the chain that, UAV moved autonomously, finally it could land almost. Okay, but as you could see that at the last moment, that it, that the flight was not under control because it was within the first 10 centimeters. When it comes to the last 10 centimeters, when the altitude get at 10 centimeters on the other word, so it loses the all the this mark detection. So then it final moment is not so good. So we are going to improve this in the future. So I think I already talked about the main stories of the presentation today. So as the final story is something related, it's also related to research, but I'm going to introduce you some research project done in my laboratory. So here I'm not going to show you very much details, but very shortly, I just want to show the project to you, that's all. So here, the project name is Audio Video Processing Based Victim Detection at Disaster Site by UAV. So actually in Japan and many other countries, some researchers are trying to use UAV to detect victims in the disaster field. Here victims are detected by the UAV and then this information are sent to the rescue team. So this is to reduce the workload of the rescue teams. So when we use the cameras, generally people on UAV cameras are used for this, to achieve this. But when the camera cannot capture the victim, that means camera cannot capture means something. If the victim is, not visible to the, is covered by some object or something, that the victim will not be captured, will not be appeared in the camera images. So I think one of our students want to give some solution for this kind of situation. He thought to give, he was looking for possibilities of using the voice. Here his voice is something that is, his idea is very simple. The UAV include a microphone and UAV, we have installed microphone and speaker on the UAV, and the speaker emits sound from the on UAV speaker, send some sound to victims to be respond. So anyone there or someone there or like that, maybe covering other or in singular or like that. So then if there's a response from the victims, that these response is captured by the on UAV, and the microphone on the UAV. So through this method, with this idea, the victim detection is conducted, and this information is sent to the rescue teams and the other parties who need the information. But here the research problem is that when the the response voice from the victims is mixed with the UAV propeller sound, as you could hear now that UAV propeller has a very very high sound. So with this sound, it is difficult to capture the sound from the human being. It's difficult to capture the human being sound by the on UAV microphone. So extracting the the victim voice from the sound mixture is a kind of going to be some research title here. So okay, so I think it's kind of I just explained about some project, that's all. Okay, so here I think today I talk about the projects, but some detail, not in very much details. So maybe if you are interested, you can look at these papers here. So about the HATR, hybrid aerial and terrestrial robot, you can a lot of information you can find from this paper. But if you are interested, if you cannot access the IEEE Explorer, please send me a message. Maybe you can get my information from Mr. Adhikari or Dr. Sagara. Maybe I can send you the paper. So about the second story, maybe still we are on the publishing process. So maybe in the future, maybe within few weeks, we can provide the documents to you if somebody are interested. So about the last project, we have already published, and so it is in the IEEE Explorer. So it is in the IEEE Explorer. So now it's already it's open access, so anyone can download anytime here in the first paper. So if you are interested, you can get the paper and read and get more information. Of course, if you like to have some question, please write message to me. So I think it's these are some latest publication. And of course, I would like to thanks to these people, and because they did a lot of works regarding this, and Malik Demirhan from now he's working in the Germany, Fosun and Aiki Ueda, and they are Japanese, and Kenki Nakanishi and Chamika Janit Pereda, he's from University of Moratuwa, and Masaya Tamaki and Seiko Epson, and Susara Tenura, he's also from University of Moratuwa. He also did some work related to these projects. So I would like to thanks to them. And today, Mr. Adhikari and the main organizer, asked me to talk about something about the COVID-19, and as well as my university information about the university. First of all, I would like to talk about about some information about my university. So here, my university name is Shibaura Institute of Technology, which is located almost near to the central Tokyo. So we have 3 campuses. One is Toysu campus, where my laboratory is also located in Toysu campus. And we have another 2 campuses in Omiya campus and Shibaura campus. So if you are interested, maybe you can search information from the online, maybe YouTube, you can see some videos about the university. So this university include, it is a kind of engineering university. Okay, I will do it. Okay, I will share it at the end of the presentation. Okay, so here in our university have 4 colleges, and one is colleges means it's like a faculties. So within 21 departments, and we have a graduate school with 253 laboratories. It include a lot of science and engineering related laboratories. Okay. So about my laboratory, actually my laboratory is under the laboratory name is Image Processing and Robotics Lab under the Graduate School of Engineering and Science, and department is Electrical Engineering and Computer Science. And in my laboratory, I think maybe through this presentation, hope you could get what my laboratory, what we are doing here. So, but in the left side, you can see some keywords of the laboratory, keyword related to the project of the laboratory. And in the middle area, you can see the some research project. Actually, some project were introduced today too. Maybe some were not introduced. And the vision of the laboratory is supporting human beings who really need support from others by IT and robotics. That's the vision of our laboratory. Okay, thank you. So again, return to the university information that our university has 4 partner universities in Sri Lanka, and they are the Wayamba University of Sri Lanka, and the University of Moratuwa, Sabaragama University of Sri Lanka, and Sri Jayawardhanapura Kotte University. Actually, me personally, I'm not a graduate of Sri Lankan University, so I made this partnership. Actually, this partnership is made through my enrollment. So in Japan, so actually I met some staff members in these universities through some events and some in some conferences, and then I asked them. Then actually many people help in Sri Lanka side to make them. So for example, like today's one of organizer, Dr. Sagara, involved in making the MOU, the partnership between my university and the University of Moratuwa. So maybe other universities also made like that. Some staff members in those universities involved a lot and helped me a lot to do this. So as a partnership, when we made the partnership, that means when you make a MOU, so we can do a lot of activities with the university level. But here our university conduct research exchange programs and a global project-based learning program. Here, that research exchange program is that the student can come to our university for a few months and they can do some research for a few months. So so far, almost all the students could get some scholarship. I could arrange some scholarship from our university side to survive certain levels, but it's not perfect, but it can cover some expenses during their stay. So these are some activities. Second one is the global project-based learning program. Is also kind of some activity we do with the partner universities. So in the first line, you can see some activity done with welcoming some Sri Lanka student teams from Sri Lanka. So and the first line, first layer of the images, you can see there are some activities done in Japan. Okay, a welcoming student from Sri Lanka. And in the second layer, you could see some activities done in Sri Lanka, taking the Japanese student to there. Actually, this is we did some events in University of Moratuwa and all the partner universities, almost all the partner universities. These pictures, I think these pictures maybe is the first event we done in the University of Moratuwa, I think. Yeah. So maybe you could see this Dr. Sudhanda sir and Dr. Sagar actually they involved, and maybe other staff members also did help me a lot. And here I think in the former vice president, vice chancellor also here. So these are some memories with Sri Lankan universities. So now I'm going to talk about something little bit about the our situation regarding the COVID-19. So here also Japan also is under a lot of problems. Still, I'm in Tokyo now, but we are under the second wave. It's very severe now. It's going to be bigger than the first wave. So, however, now we do all the duties in the university, and all the lectures are going to be online. But before we start online lectures, we did some survey. Maybe you don't believe it, as according to our first survey, that almost like 20% of students did not have some internet facilities at homes to receive online lectures. Hope you may not, maybe you don't believe it, but the situation is real. The reason is that internet service data is not enough. That's one of the major reasons for this. And some of them didn't have computer computer or tab at home or with them. So, but they have smartphones, but but they didn't have a computer. I think without having a computer or tab, it is a little difficult to, receive some online lectures. So our university decided to make some solution for these problems. University grants scholarship to prepare enough internet facilities for those students do not have online internet services. So however, this is in here Japan, that is you cannot compare this with some Sri Lankan universities, because in Japan is my university actually it's a private university. Even in Japan, even though university is government university, the tuition fee is there. University charge a lot of money from the student. So university management is done by using those money. So in this time, this scholarship is granted using the money from student as well. So we cannot compare these issues with Sri Lanka. So the second solution the university did is we lent the university computers to the student. I don't know whether they will be back or not, but we lent it. So someone asked, someone need a computer. So we lent the computer. So someday please return. We asked our target, because within university we have a lot of, within university there are some, in the computer rooms and some other laboratories we have computers, but within the, when we conduct the online lectures, sometimes we don't need it because no one use it. So university decided to lend to the students. But I know arranging this is very difficult, but a lot of things had to be done. It's not easy task, but finally we did it like that. I think that when we are conducting online lectures, I think there are some, of course, there are some weak points of the online lectures. The lectures, some lectures can be conducted, but as you know, maybe you may have done some, if you are from engineering or science faculties, you have some, experiment subject, some experiment with the big machines and something like that. So these experiments cannot be conducted. This is so it's a current solution is we, some, staff member or some teaching assistant or research assistant do the experiment and send a video of the experiment and the data to the student and ask student to submit a report. This is the current solution. I think this is not very good. However, if you have any interesting idea about interesting solution for this problem, maybe I would like to glad to get information from you too. So in my laboratory, we have not stopped any research supervision. Even, now people are, here, it's going out is very danger. So most of the people are staying at home, but, some, people, some due to some, works and some reasons, people go out. Here we conduct a research supervision. It's almost online. So in my laboratory, that the student cannot use the laboratory right now, that, so all the students work at home. So we have some discussion and arrange some research topic. Those can be conducted at homes. And in our university, we talk with the university and we made some, for a certain level, we allow the student to buy some necessary stuff to carry on the research from the university money. And other thing is we do all the online, all the supervision in online. And in my laboratory, I have arranged some online research progressing environment. This means that we meet, all the students meet online for a few days per week, and we each of them progress their own works on research projects and communicating each other online. Okay, so it's some environment like that. They are working at home, but we are connected each other in the meeting online. So these days, I'm not asking student, I'm not encouraging student to submit to research findings to the conference much, because attending a conference is very difficult. But these days I'm asking student to submit research findings to the journal. So finally, actually about Sri Lankan side, actually I did some activities during the COVID too, but it's very simple one. So maybe you could also see some invention during this COVID. In Sri Lanka, I could see a lot of invention, a lot of product to support medical sector and some other parties, who really care about the COVID patient, like military and some others, And we could see many inventions from some inventions and product from university student and school student and some other parties. I think encouraging and supporting them to improve their product to make the business is important in the future. I think this is something we can get from the COVID-19, because we lost some, we have lost during the COVID, but we have to think what to get after the COVID. I don't know whether Sri Lanka now is after the COVID. I'm worried about Sri Lanka too, because I cannot still some patients have been in some places. So I made it again mute, and this is some kind of activity I did with Sri Lankan student, but his name is Nidapul Senaviratna from Mie University of Sri Lanka. He made some automated hand sanitizer machine to use in IDH hospital and some other hospitals in Sri Lanka. Actually, he brought this proposal to me and his supervisor in Mie University of Sri Lanka. His name is Dr. Susanta Vijayasinghe, and he was supported. This work was supported by a doctor in Pandra Hospital as well. And this is a machine he made, and now it is used in some one of the important hospital, IDH hospital in Sri Lanka. Actually, from my side, I give some technical support and maybe some advices, and finally I give some donation to make machine to donate to some hospitals. Maybe you can see the machine here, like what kind of machine it is. He said that it can, the machine, you can fix all the sanitizer bottles in Sri Lanka to this machine very easily, and you don't need to touch the bottle at all. So that means it can be used in that way. I think this machine, I think this is very much helpful in the hospital like IDH hospital in Sri Lanka. Yeah. So again, I think supporting, encouraging is this young generation is very important, and to make their bring their product to the business level. So this is the end of my presentation. Thank you very much. And I got in the chat, I got a question to share the papers. Okay, I'm going to share the papers here, the sites of the papers. So if you have any, educational research purpose. Oh, I guess so the thermal imaging is restricted. Actually, in my presentation, I got a comment like the thermal imaging is restricted for use in UAV for educational research purposes. Yeah. So actually, in this my presentation, we don't use any thermal imaging. We only use some general image. Okay. So then I got a question like, could you please share the link related to the mentions papers? Okay, so I will share it now. Give me 1 minute, 2 minutes.
In the meantime, can I ask a question, Professor? I'm Danushka, joining from Estonia, but I'm Sri Lankan.
Okay, great.
Yeah, so it's very interesting to see your presentation. And did you consider using any kind of infrared cameras or spectral cameras to detect humans for your third project?
Yeah, actually, we are thinking about this to use some spectral cameras. Okay, but so far we don't have experience in using that.
Okay.
Okay, I think it's. I think maybe we can think about. You can think about some new research direction with the spectral camera with UAV. But however, I could see some papers in the literature. Maybe I recommend you, if you are going to do such kind of research, better to look at the papers, what's already done, and then you can think about some new directions like that.
Yeah, definitely. Because at the moment, I'm PhD student.
Okay.
I'm working on hyperspectral imaging.
Oh, great.
Yeah, pretty much what we are dealing with is visible light range infrared hyperspectral cameras.
Okay.
But not in short wave or long wave infrared.
Oh,
but
okay.
We did something with long wave infrared, but it's not for human detection. Obviously, I know that if you use this long wave infrared, which means the thermal camera, then you can do quite a bit of detection. But it might be more effective than using speech, I guess, or the sound or audio detection.
Yeah.
What do you think?
Yeah, I think, yeah, but first of all, I think in my side, actually, I'm trying to say that as I mentioned, that we have not done any experiment regarding this. So it's a little, difficult to comment on your question, give some comments. But I think there are some possibilities. I cannot say no.
Okay, great.
Okay.
The next thing is that I whether maybe I missed it, but are you using Raspberry Pi for completely all the flight controls and machine vision and everything? So
Okay.
how you do it?
Here that what do you mean? Like here in my presentation in this project we have not used any machine vision. Okay, so we have made the algorithm is as simple as possible. It's kind of image processing algorithm. Okay, however, in my laboratory, my student tested some some machine vision algorithm with the Raspberry Pi with some neurocomputing stick. And the Raspberry Pi, the Raspberry Pi 4 works very well with the neurocomputing stick.
Okay, right.
Okay, right. So if you want to try it, maybe you can try it. I think I recommend you to use the Raspberry Pi 4 because Raspberry Pi 4 is better than Raspberry Pi 3. Okay,
definitely, because we got it. And also one suggestion, because right now there are several UAVs even we got for our labs that I think they are using vision processing units, not like SoCs what we have in Raspberry Pi.
Okay.
GPUs, but something in this direction. But just to ask whether you have any research or anything, any ideas going on in this direction. For example, getting.
Yeah, I think it's a good direction. Point is that how you connect this, some hardware with for other purposes. For example, in the case of drone control, that we can use, we can do the vision processing with that those kind of hardware. Okay, so then we have to search that whether it is possible to do the autonomous controlling parts and some other conversion part with the same hardware.
That's
it's become very important. Okay, but if there's a hardware that we can add some newly processing parts, okay, so then it's going to be okay.
Right. Yeah. Thank you very much. Thank you.
Okay, thank you very much. So I already add one paper. Maybe I'm going to add some second paper, but second paper is not in the IEEE Explorer, but in the IEEE Explorer, but it's not open for the world. So I have the second one. Maybe these papers are most related to the this research.
Sir, I have a small question.
Okay, great.
Yeah, so you told there aren't the neural-based image recognition algorithms used much in the project you showed.
No, actually this time we have not to use a neural network. Actually, we tested with neural network. We can, conduct the detection process. Okay, but the problem was it was not much real time. Actually, our target was to, detect the landing spot within 20 milliseconds. Okay.
Yeah.
So we could not achieve it. Actually we tested it. A few months, maybe 1 year before. I don't remember exactly, but maybe with the current hardware, maybe, okay? With the current hardware, you may be able to do, because in our project, we do all the processing on board, okay? On the drone, on the UAV, okay? So to do this, to achieve this kind of on drone process, but if you use very big hardware, we can do it, okay? Real time. But point is, we cannot install those big hardware on the drone, okay? Not drone is it's not possible to install a big hardware on the drone, okay? So I think I recommend you to test with latest hardware, with some processing. But it's the image processing time is depend on some depend on the processing we are going to do, type of the processing. If the processing algorithm is quite complicated one, then it's going to be a lot of going to be time consuming. Okay, is it okay for you, your question?
Yeah, thank you.
Okay, do you have anything to be clarified?
So sir, what do you think would be the effect of using like is there any way to optimize or in a way compress the algorithm, like neural based algorithm, so that they would fit in and they would work in an optimal manner within the board?
Yeah, I think one of our students did some project that what they did is they the neural network, what they did is that they, compact the, model of the neural network. And actually they publish a paper with that, okay? So if you think this direction, you can have a, less time consuming models, then, you can do it.
Thank you, sir.
Okay. So I got a question, ultrasonic distance sensing. Okay, wait a moment. This, I think, by using ultrasound distance sensing is okay, but we can only measure the, head. Head means only the altitude. We can measure with the ultrasound sensing, but it's difficult to get some, XY directional information while we are going to make some autonomous flight. Okay. So next one is how increase FPS in Raspberry Pi. We cannot, FPS is a frame, maybe your question is related to frame rate of the camera. Okay, I think in the Raspberry Pi, we can, maybe you are talking about the camera image capturing or the processing. I'm not clear, but if it is related to the image capturing, then generally in the Raspberry Pi, the camera which are compatible with the Raspberry Pi hardware has the frame rate of 30 FPS. So you can take the images with this frame rate, but 30 FPS is like, so almost each 33 millisecond you get an image. Okay, so that means if you want to do some real-time processing that you have to do within, the algorithm should work within 33 milliseconds. 32 means I think it should be work within 28 milliseconds, I think. Okay. So if your question is related to like that, my answer is like that. And if it is like, Raspberry Pi itself cannot, improve the, frame rate of the camera, I think. Okay. Guess it's possible with the LiDAR trans. Yeah, I think it's we can use LiDAR, but good question, LiDAR under that drone, and I think your question is okay. But point is when we use the LiDAR, still the LiDAR sensors are, have some weight. It's not lightweight yet. Maybe if I think recently I found some lightweight LiDAR, but we have not tested. But when the hardware becoming light, even in the LiDAR, it is lightweight, so we can use it easily. Because as I mentioned in the presentation that when we use when we install some hardware on the drone, we have to be careful about the weight of the hardware as well. Okay, then Deshita. Okay, I think Deshita, you could okay with that. And then FPS can't increase unless you improve the right. Okay, so I got the thing. That is, yeah. So that point is that answer was maybe Danushka. The answer is I already, as I said now. So if you want to keep the FPS same as your camera, camera image capturing FPS, okay. If it is 30 FPS, that you have to, if you want to keep it a real time, that you have to make the processing with it like 30 milliseconds, because if the camera is 30 FPS, that you get the image within each 33 milliseconds. That means if we could process the image in each 33 milliseconds, then we can make it real time. Other time there's some confusion there. Okay.
Yeah, again, sorry to interrupt once more, but just I can add a little bit of comment about the LiDAR.
Okay, good, great, thank you.
Yeah, we recently did a LiDAR testing with solid state LiDAR, which is very light, roughly around 200 grams.
Okay, great.
With the electronics and all the stuff, it came around roughly 800 grams.
Okay, okay.
But the detection range was so low, less than 10 meters.
Okay, okay.
If you're flying really low, then yes, it works perfectly fine.
Okay.
And the processing speed also quite considerably low. Like you can, it's not really good to use this kind of solid state LiDAR or anything at the moment, because we found kind of latest version where it's cheap from China.
Yeah. But I think it's quite expensive, It's like I don't know. It's maybe I saw the maybe LiDAR camera maybe online. Maybe it's like maybe I don't know exactly like $500 or something like that.
Yeah, so something around like
okay.
300. And then Intel also recently released their RealSense LiDAR and camera module together.
Yeah. It's a kind of some cylinder, small round cylinder.
Like
Okay,
yeah,
okay,
like
okay.
a hockey puck kind of small thing.
Okay, okay, okay. Got it, got it.
Yes,
But,
but this range also really low.
okay.
And we are playing with that. I'm not sure even we can use it in real
All right.
life.
So, how about the, according to your experience, how about, it's something like frame rate or something, data, how fast it is, like data,
Yeah, the bandwidth and all the stuff, because it uses a USB 3 interface, so you
Okay.
can have the bandwidth, but when you process and convert, you can't really get these 20 frames or
Okay.
30 frames rate to match with your control algorithms, because that's
Okay.
the
Okay.
end of the day. You can't do it. Yeah.
Okay, thank you. It's a very, very good information. I think it's like $40. Yeah, maybe I could see it, but recently I saw the information, but we have not done anything regarding. But we used the big camera from RealSense. Quite we have done some research, but they are only for with some wheel robots, but not with drones. Why we didn't use drone is we tested the normal real sense camera, that the one is bigger one, and we found that it's very difficult to make the processing real time, like within 20 millisecond, so that's why what we suffer now. Then maybe as you said, actually we tried to have processing with a Raspberry Pi 3B, but maybe if we can find if they release a more proper hardware, maybe possible.
Yeah, but what we tried is NVIDIA. It's called Jetson Nano.
Okay.
Jetson and Jetson Nano both. So Jetson Nano is like $100 GPU-based computer, but it gets really hot when you try to.
Hot. And actually, we also, I think maybe almost 1 year like that, we did also some experiment with that. But all are doing same. But I think there was some problem, because actually I don't remember exact information that they said that it's really difficult to have some real time processing or something like that. That's why our student give up it.
Yeah, exactly. And also calibration really hard, and we really had a hard time with that. So I can't recommend it to do it. But on the other hand, if you work with these professional drones, so these ones like the DJI Mavic and Matrix, they are using stereo vision to obstacle avoidance. Even we had the Mavic Pro and also Matrix. Both of them use vision for landing and also obstacle avoidance, but they don't use this kind of GPUs, but they use VPUs, vision processing. They have dedicated hardware that we can't really get.
Yeah, actually, it's a kind of very big company. They have some.
Exactly. So you can't compare.
Yeah, it's when you do something within our laboratory, it's quite it's a lot of difficulties. Like.
Yeah, exactly.
The stereo vision means we have to process the information from images from two cameras. It's generally little. There's some computational, some complexity, and we have to think how to make it real time. But as you said, that there are some product with some the drone with the camera, and it has autonomous landing functions now.
Yeah, it's really competitive, and also it's not worth to fight with large companies, because they are pumping a lot of money. So thank you for your time, by the way.
Okay, thank you very much. So I got a question about I'm undergraduate in information system in State University, but I want to be Robotics part. This is I think you can get a contact. You can get some information from Mr. Adhikari today. Maybe I can then I will maybe we can have some communication. Okay, thank you. So how about you, your side? Is there any questions? So I think you are going to have your dinner. Here I already have my dinner, and maybe it's going to be 11 p.m. here time. So 10:45 now. I hope so. Everything you are all okay, no? Any questions? So I have put the links of the papers just now. And finally, again, I have I put some links of the Google form to the mouse electronics participants. So maybe please follow this survey. Okay. So you can get information from Mr. Adhikari, maybe the organizer of the this event today. Okay. I think is it okay? So. Okay, Taridu, shall we finish the event today? So again, I put a survey on the, in the chatting about to the Mouse Electronics participants. Okay. So thank you very much for attending this event today. And I would like to thank all the related people to this event, and especially Mr. Adhikari and Dr. Sagara to arrange this. Okay. So thank you very much again. Okay. So I'm going to finish the meeting. Okay. So thank you very much. Good night to all of you.